Hello friends, welcome to this YouTube channel. Today we shall solve a couple of simple numerical problems on DC generators utilizing its EMF equation. This is a 4-pole stator structure of a DC generator. For general case, let us assume total number of poles be P. If field windings are placed on these distinct poles and DC excitation is given to them, electromagnets will be formed. These electromagnets will produce a static magnetic field. If armature is placed in this magnetic field and rotated by some external prime mover, armature conductors will experience a time varying magnetic field. Let us assume the speed of armature be n rpm. Therefore, time taken to complete one revolution delta t equals to 60 by n seconds. If we consider a single armature conductor, after one revolution it will experience change in flux delta phi equals to p times phi. According to Faraday's law, EMF induced per conductor will be EC equals to delta phi by delta T, that is equal to P phi into N by 60. If total number of conductors be Z and total number of parallel paths be A, then number of conductors per parallel path will be Z by A. Therefore, induced EMF E equals to Pn phi Z divided by 60A. For lap connected armature, number of parallel paths A equals to P, and for wave connected armature, number of parallel paths A equals to 2. Problem number 1. A 4-pole wave connected armature in a DC generator has 51 slots with 12 conductors per slot. It is driven at 900 rpm. If the useful flux per pole is 25 milliweber, we have to determine the value of generated EMF. Let us first jot down the given data. Number of poles of the machine P equals to 4. Useful flux per pole phi equals to 25 milliweber. Speed of the rotor N equals to 900 rpm. Number of slots S equals to 51. Conductors per slot Zc equals to 12. Let us first calculate total number of conductors. Z equals to S times Zc, that is equal to 51 into 12, that gives us 612. Expression for generated EMF E equals to phi Z Np divided by 60A. For wave connected armature, number of parallel paths A equals to 2. Therefore, generated EMF E equals to 25 into 10 to the power minus 3 into 612 into 900 into 4 divided by 60 into 2. That gives us 459 volts. Problem number 2. An 8-pole DC generator running at 1200 rpm and with a flux of 25 milliweber per pole generates 440 volts. We have to determine the number of conductors if the armature is lap connected and if the armature is wave connected. Let us first jot down the given data. Number of poles P equals to 8. Flux per pole phi equals to 25 milliweber. Generated EMF E equals to 440 volts. Speed of the rotor N equals to 1200 RPM. Expression for generated EMF E equals to phi ZNP divided by 60A. Therefore, expression for total number of conductors will be Z equals to 60AE divided by phi NP. For lap connected armature, number of parallel paths A equals to P equals to 8 for this machine. Therefore, total number of conductors Z equals to 60 into 8 into 440 divided by 25 into 10 to the power minus 3 into 1200 into 8. That gives us 880. For wave-connected armature, number of parallel paths A equals to 2. Total number of conductors will be Z equals to 60 into 2 into 440 divided by 25 into 10 to the power minus 3 into 1200 into 8. That gives us 220. If we compare both the cases, we can conclude that for wave-connected armature, number of conductors required is 1/4 of that required for lap-connected armature for the same amount of generated EMF. Problem number 3. An 8-pole DC generator has 500 armature conductors and a useful flux of 0.05 Weber. We have to determine the EMF generated if the armature is lap connected and runs at 1200 RPM. We also have to determine the speed at which the armature is to be driven to produce the same amount of EMF if it is wave connected. Let us first jot down the given data. Number of poles P equals to 8. Useful flux per pole phi equals to 0.05 Weber. Speed of the rotor N equals to 1200 RPM. Number of armature conductors Z equals to 500. For lap connected armature, number of parallel paths A equals to P equals to 8 for this machine. Expression for generated EMF E equals to phi ZNP divided by 60A. Using values, we get 0.05 into 500 into 1200 into 8 divided by 60 into 8. That gives us 500 volts. For wave-connected armature, number of parallel paths A equals to 2. In this case, generated EMF is same as before, that is E equals to 500 volts. Expression for speed at which the generator is to be driven N2 equals to 60 AE divided by 5 ZP. Using values, we get 60 into 2 into 500 divided by 0.05 into 500 into 8. That gives us 300 RPM. If we compare both the cases, we can conclude that to obtain the same amount of generated EMF, wave-connected armature is to be rotated at 1/4 of the speed at which lap-connected armature has been rotated. Problem number 4. An 8-pole DC generator has 200 armature turns and runs at 1500 RPM. The EMF generated on open circuit is 400 volts. We have to determine the flux per pole when the machine is lap connected and when the machine is wave connected. For the same value of flux per pole as in case 1 and considering lap winding, we have to determine the speed of the generator to generate an EMF of 600 volts on open circuit. Let us first jot down the given data. Number of poles of the machine P equals to 8. Generated EMF E equals to 400 volts. Speed of the rotor N equals to 1500 RPM. Number of armature turns T equals to 200. Total number of armature conductors Z equals to twice T, that is equal to 2 into 200, that gives us 400. For lap connected armature, number of parallel paths A equals to P equals to 8 for this machine. Expression for generated EMF E equals to phi ZNP divided by 60A. Therefore, expression for flux per pole phi equals to 60AE divided by ZNP, that is equal to 60 into 8 into 400 divided by 400 into 1500 into 8, that gives us 0.04 Weber. For wave connected armature, number of parallel paths A equals to 2. Flux per pole phi equals to 60AE divided by ZNP, that is equal to 60 into 2 into 400 divided by 400 into 1500 into 8, that gives us 0.01 Weber. If we compare the required flux per pole for both the cases, we find that wave connected armature requires 1/4 of that required by the lap connected armature. When generated EMF E2 equals to 600 volts and armature is lap connected, number of parallel paths A equals to P equals to 8. Speed at which the generator is to be driven N2 equals to 60A E2 divided by phi ZP, that is equal to 60 into 8 into 600 divided by 0.04 into 400 into 8, that gives us 2250 RPM. Problem number 5. A 4-pole DC generator has 1200 armature conductors and generates 250 volt on open circuit when running at a speed of 500 RPM. The diameter of the pole shoe circle is 0.35 meter and the ratio of pole arc to pole pitch is 0.7, while the length of the shoes is 0.2 meter. We have to determine the mean flux density in the air gap. We have to neglect the shunt field current and assume lap connected armature winding. Let us first jot down the given data. Number of poles of the machine P equals to 4. Generated EMF E equals to 250 volts. Speed of the rotor N equals to 500 RPM. Number of armature conductors Z equals to 1200. Length of pole shoe L equals to 0.2 meter. Diameter of pole shoe circle D equals to 0.35 meter. Ratio of pole arc to pole pitch equals to 0.7. Therefore, pole arc equals to 0.7 into pole pitch. Let us now determine pole pitch, that is equal to pi d divided by P Using values, we get pi into 0.35 divided by 4 meter. Using this expression, we get pole arc equals to 0.7 into pi into 0.35 divided by 4. That gives us 0.1924 meter. Pole shoe area AP equals to pole arc into pole length. That is equal to 0.1924 into 0.2. That gives us 0.03848 meter square. For lap connected armature, number of parallel paths A equals to P equals to 4 for this machine. Expression for induced EMF E equals to phi ZNP divided by 60A. Therefore, expression for useful flux per pole phi equals to 60AE divided by ZNP. Using values, we get 60 into 4 into 250 divided by 1200 into 500 into 4. That gives us 0.025 Weber. Flux density in the air gap B equals to phi divided by AP. That is equal to 0.025 divided by 0.03848. That gives us 0.65 Tesla. So today we have solved a couple of simple numerical problems on DC generators. We have learned how to determine flux per pole, number of armature conductors, speed of the armature, etc. of a DC generator using its EMF equation. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.